What again? Today we're going to do this problem right here, number 10. I'll put it up on the screen right now. Basically what we have is a rod, rigid rod, with a ball being held by two strings. They are both length L, and they are separated by a length D. Then this rod spins around like this, so that this ball reaches a tangential velocity of 3.00 meters per second. Is that true? 3.00 meters per second. The length over here is 2.00 meters, and the distance D is 3.00 meters. And also we're given the mass of this ball, which is 4.00 kg. So it says, why is the following situation impossible? The object of mass m in this figure attached to a vertical rod by two strings of length L, 2 meters. The strings are attached at this point, a distance d, 3 meters apart. The object rotates with in a horizontal circle at a constant speed of 3 meters per second, and the string remains taut. So that's an important thing. The strings here remain taut, meaning they are being pulled tight and there's no slack or anything. The rod rotates along with the object so that the strings do not warp around the rod. Why is this situation impossible? So we have to figure out what about the situation makes it impossible. And the first thing I'm thinking about is sum of forces. So sum of forces equals MA. We have sum of forces in the y direction, and we have sum of forces in the x direction. In the x direction, there's actually centripetal acceleration. So we also need this equation, right? And this r is this distance here. This is the distance r, because this thing rotates around in a circle with the radius r. So automatically I should find r, but I'm given d and I'm given L. But here I have a right angle triangle where one side is d divided by 2, right? Half of this distance. And then the length here is 2 meters. So I can do Pythagorean theorem to find r. We should probably do this right away because I think it's going to be useful. But let's just set up the equations. How do you set up the equations? You look at this object and create a free body diagram. So here is the ball. In the y direction, it is being pulled up by the string. So this is the y direction. The string is pulling it up this way. Let's say this is tension, and there's another string pulling it down this way. This is tension 2. Maybe we can call this T1 and T2, and they should be the same length. And then there's also an mg force pulling it inwards, and I think those are all the forces. There's also this centripetal force kind of pulling it out, or you could look at it another way. In the x direction, there is centripetal acceleration. So I'm going to leave it like this. But we should also split apart these forces. The tension of string 1, we should split it up into the x component and the y component. The x component and the y component. And the tension 2, we should also split up in the x component and the y component. So I will probably do this live, but let me find this r here. So Pythagorean theorem, a squared plus b squared equals c squared. And we have here r squared plus d over 2 squared is equal to L squared, right? This is the hypotenuse of this triangle. This is one leg of the triangle, d over 2, because this distance I have, and then this is the other part. So I can isolate for r and see that this is, d is 3, so this is 1.5 squared. Actually, it's this minus this, so I should make a little correction order. This L is 2 meters, so 2 squared minus 1.5 squared. And this is the length of r. And I think I calculated it. I'm gonna try to remember. This is just 1.3 meters. 1.3 meters for r. Another thing that's interesting is one of the angles over here. So I chose this angle here, theta. You could choose any angle, but if I have this angle, then that is the angle over here. And and over here because the scenario is symmetric. So if you have these two angles, you could split up the tension of this guy into the y and the x component, which is pretty useful. And I think I calculated this by doing, let's see, it was sine. So sine is opposite over hypotenuse. Here I have d over 2. D is 3 meters, so 1.5 meters divided by this. And sine of inverse gives me this theta as 48.6 degrees. Nice. All right, now I'm going to just simplify this free body diagram and draw it over here so it looks a little bit more clean. In the y direction, I can split up this tension 1. It will be tension 1 times, this is the opposite over hypotenuse. So that is sine of theta. So that's tension 1 pointing this way. There's also tension 2 pointing down this way, right? This tension 2, I split it up into its y component, and that's also the opposite over hypotenuse. So that would be T2 sine theta. I also don't know if the tensions are the same. The rope here could be pulling more here, and over here could be like pulling less, right? The tension is not going to be equal unless the speed is like infinite or something like this. So those are the two, and we also have two x components for the T1 and for the T2 pointing in this direction. So I'm just going to draw this, and then another one. This is T1 cosine theta and T2 cosine theta. I drew them the same, but they could be different depending on T1 and T2. Then we also have the mg. I'm just going to draw it slightly bigger here. Mg. So these are all the forces. From here, I can create the sum of all forces equals ma. Let's do it in the y direction. So in the y direction, I have T1 sine theta pointing up. T1 sine theta pointing up. T2 sine theta pointing down. And then also mg pointing down. So that's why these guys have minus signs, because they're pointing down in my coordinate system. The ball, we're assuming, is not moving up or down, so its acceleration is 0. So sum of all forces equals ma, which is 0. So this is the first equation that is pretty important. You can maybe simplify it a bit by factoring out these signs. Sine theta, T1 minus T2. And then move this mg on the other side equals mg. So this is an important equation for the y direction. For the x direction, if we add all of these, let's say this is the positive x-axis. Normally we have positive x-axis here, but since both of our forces are pointing this way, I'm just going to make this the positive so I can add these two together. And I'll also factor out the cosine. So I have cosine theta, then T1 plus T2. And those are all the forces here. So sum of all forces looks like this, equals. In this case, it doesn't equal 0 because it feels the centripetal acceleration here. So instead of equaling 0, we're going to say it equals ma, which is mv squared over r, like that. And that's also an important equation. Okay, so what do we do with these equations? We're trying to answer if this problem is possible. And I'm not sure exactly how to do that, so I'll just try to solve for these tensions. Because right now, these are the only unknowns. We have theta, it is over here. We have the mass, the velocity, and the radius of the thing, and we have this g. So we have everything in these equations except the tensions. So if I solve for the tensions, maybe something interesting is going to come out of this, and we can see if we get an answer. But that being said, I think I'm going to erase this and continue writing on this side of the board, so I'm not like going out of the page here. But I'm going to keep these two numbers because these numbers are important. So one mistake I made before was I tried to divide two equations. Yeah, I think what I did was divide this equation by this equation. Sine divided by cosine is tangent. But then we get some messy stuff in here. And I think the way the book does it is they move this sine onto this side by dividing both sides by sine. They move this cosine onto this side by dividing both sides by cosine. And then they add and subtract these two equations. So I will do that over here. T1 minus T2 is equal to mg over sine theta. I believe this is what the book was doing. I tried it my own way and kind of got into a pickle by dividing the two equations, so this is why you should try the problem out on your own and then also see if the book has a different way of solving it than r cosine theta. So now you have these. If you add this equation to this equation, I have T1 minus T2 plus T1 plus T2. There's a minus T2 and a plus T2, so these cancel. So you kind of isolate, like you eliminate T2 and you isolate for T1. And then you can add stuff on this side. So I'm going to do that. If I add here, I will have T1 minus T2 plus T1 plus T2. I'm putting brackets like this, just because I'm showing that I'm adding this equation, then I'm adding this on this side of the equal sign. You can add equations together, that's okay. If this side is true, and this side is true, and this side is true, and this side is true, you can add them together, and you'll get something true as well. So here what we get is mg sine theta plus mv squared r cosine theta. And then here you can see what happens is T1 minus T2 plus T1. So T1 plus T1 gives you 2T1, and then the minus T2 plus T2 cancels out the T. So what we get is 2T1. If you subtract the equations, so I take this equation minus this equation, I cancel these guys out, and I get minus 2T2 on this side, minus 2T2. And then the same thing happens on this side. All that changes is a minus sign over r. Here's a minus sign. Cosine theta. So this is just how I piece the equations together, or how the book does it. If you divide both sides by 2 here, and you divide both sides by negative 2 here, you get the tension 1 and the tension 2. And then here you have the mass, right? The mass is 4 kilograms or something. You have g, you have mass, you have v squared. You can find sine of theta, just plug this theta in. This is the theta that we were talking about from the free body diagram that we drew before. We have r, 1.3 meters, and we have cosine theta. Plug this in, you can get an equation for, you can get a value for T1 in newtons, if everything here is in SI units. And here you can get the same thing. So I'm going to erase that here, and you guys can do the calculations on your own. I will just show you what I got at the end, and we can talk about it. So for T1 I got minus 5.7 newtons. For T2 I got 46.9 newtons. So keep in mind what the picture was talking about. We have a rope here, and this, and a ball. This was T2, if I'm not mistaken. I kind of erased my diagram, but I'm hoping this was the T2. And this, I think, was the T1. So we can see that T2 is pulling more, right? This is a bigger number than this one, which makes sense. Like, if this ball was not spinning at all of the weight of this ball would be on the tension of this string. But now it's spinning, so maybe some of the tension is here. But here's why it's impossible. This tension is pulling this way, right? This is how we defined it. This is the positive direction. If there is a tension pointing this way, this would be in completely negative of this number. So this tension is this number, positive, makes sense. But this is negative. So the way we set it up, we said the tension was pointing this way. But what we got was actually a minus sign. So it's as if the tension was actually pointing this way. That's what this minus sign says. And it's a small number here. So the reason this scenario is impossible is because given all the numbers that were given, the speed, the distances, the mass of the ball, gravity, right? The G over here is 9.81 for Earth. We get a negative tension on the bottom string. So what this negative tension means is this is not a bendy rope. It's like a rigid rod that is pushing the ball up this way. So the only way for this to work is if this was a rigid bar and not a rope. But then the problem asks you, what if G was different, like let's say G was smaller than 9.8 meters per second, like you do this experiment on the moon or on Mars, you might get a different number. So try to work that out. Let me know if you have any questions about this. And even though I showed you kind of a solution of the problem, try to do it yourself with no help. And then if you run into a problem, look at this video or look at a solution. And thank you for watching.